So this is for statics, engineering science 2113, and this is from section 2.9 in our Wiley text. And this is the example we did not make it through class today. So we're just going to walk back through how to find the XYZ components of everything, quickly sum forces, which is what we did in class, and then look at summing moments. So we want to replace the two forces and the negative wrench, which a negative wrench. So it's got a force vector and a moment by a single force R applied at A and the corresponding moment. Okay, so it's like what we did when we were in 2D, but we're going to be walking through the 3D. Okay, so again, let's start with this 700 newtons, and it's going to have a component in this direction and in that direction. And so I can see this is in the XZ plane. So once again, note what are axes, the orientation of our axes. And so I can see quickly right here, this is 700 newtons, cosine 60, and this is 700 newtons, sine 60. Okay, this is totally in the y direction. If we wanted to write Cartesian vectors, we could write Cartesian vectors describing, and then as we're summing forces, we just look at the x, y, and z components. So if I wanted to look up here at this one, I could write that we have negative 700 cosine 60i plus 0j plus 700 sine 60k newtons. Okay, so as we're summing forces x, y, z, we don't have to do as much thinking. So now let's deal with this guy. So I'm going to pull over another sheet of paper and we're going to just look at it. This force is not only is it in the xy plane swinging at 45 degrees, it's then this xy component is swinging up. So it's one of those two angles describes the 3D force. And this is, there we go, okay? So I'm going to look down here in this plane first. So if I look down here at this plane, so I have my y and I have my x. I can see, I don't know which is the best way to do this, I can see that we are swinging in the xy plane at 45 degrees. So we're not even looking at the z factor yet. So if we look at this, okay, I'm going to have a y component and an x component in this xy plane. So we have sine 45 and cosine 45. And again, this is going to be the y component and this is going to be the x component. Okay, so that is taking part here in the xy plane. But we have to realize this plane's actually being swung up. So now we're going to swing up into the z plane. And when I look at this, okay, so here's my xy plane. This is also 40 degrees. So if I ignore the xy plane right now and I just look at this right triangle, so this right triangle is in the xz plane and this right triangle is in the xy plane. Okay, so if I look at this, I have sine 40 and I have cosine 40. So this is the xy plane and this is the z plane going up. So if I want to look at the x component of this force, it is going to be 500 newtons. That's my actual force vector times x component is down here, xy plane, so cosine 40, that gets me down to the xy plane, and then sine 45, that gets the component now that I'm two-dimensional in the xy. So cosine 40 takes me out of 3D, puts me back on the xy plane, and then sine 45 is the xy plane. So if I look at the y component, it's going to be 500 newtons. Okay, I have to get out of the 3D plane. And now that I'm out of the 3D plane, I am cosine 45. Okay, and then the z component is just 500 sine 40. Okay, if I take that away, the z component is not down here in my xy plane. So that's how I can walk through the x, y, and z. Okay, so I'm going to come back over here and I'm going to try to draw that in. And I can see that I have a y component, which is 500 newtons, cosine 40, cosine 45. I have a z component, which is 500 newtons, sine 40. And then we have this x component going back. 500 newtons, cosine 40 to get it out of the xz plane, and then sine 45, that takes care of our component in the xy plane. Okay, so we now have our forces broken down. Again, I could write this as a Cartesian vector. I could have, where's the x? Negative 500 cosine 40 sine 45i plus 500 cosine 40 cosine 45j plus 500 sine 40 newtons. Okay, so now when I'm summing x components, it's really easy to just take each of my Cartesian vectors and sum them up. So if we need to find a resultant applied at A, the first thing we need to understand is that our resultant is the sum of our force vectors, which we get from summing forces x, summing forces y, and summing forces z. Okay, let me move that out of the way. It's distracting. So I'm going to sum forces in the x direction. I'm going to call positive in the direction of my positive x-axis. So if I come up here and look, I can either look at my figure and I can see, okay, that's acting opposite. So negative 700 newtons cosine 60. And then that's a y. Here's minus 500 newtons cosine 40 sine 45. And I can find that my resultant in the x direction is negative 712 newtons. Okay, so it's acting, pulling back into the page. Or if I want to look at Cartesian vectors, I can just take my x, my x, my x, and sum them up. So now I'm going to sum forces in the y direction. I'm going to follow the positive y-axis. Positive y-axis. So this is the resultant in the y direction. So this force up here only has xz. We have a 600 newtons plus 500 newtons cosine 40 cosine 45. Again, I could just come back to my Cartesian vectors because these are the components, and I can sum up using my Cartesian vectors. So this is going to be a resultant of 871 newtons in the y direction. So this one's acting positively. This one, if we want to know, it's acting kind of back. And we can sum forces in the z direction up positive. That gives me my resultant in the z. So I can come here and look, 700 newtons sine 60, 500 newtons sine 40, 0. Or I can go back to Cartesian vectors, which again is just the components, and look at those to sum up. So I have 700 newtons sine 60 plus 500 newtons sine 40, plus 0 if I wanted to add that third one in. And I get that my resultant in the z direction is a positive 928 newtons. So the resultant is negative 612i plus 871J plus 928K newtons. I can find the magnitude by using Pythagorean theorem, and I get 1,416 newtons. That would be the magnitude if we were asked for the magnitude. And again, if I'm looking at point A, so here I'm at point A, what this is saying is that in my XYZ plane, I am walking back 612 steps. I am walking to the right, following the y-axis positively, 871. And then I am marching up 928. So my vector is pulling kind of to that back right quadrant of my system. I could find my cosine angles. I could find my theta x, my theta y, and my theta z. Because those direction cosines, theta x equals inverse cosine of component over magnitude. And if I work that out, I get a theta x of 116 degrees, which makes sense. I'm not in the positive direction. I've circled back past 90 degrees and I'm coming off the negative x-axis. I could find the direction cosine for y, inverse cosine of 871 over 1416. My units go away and I get 52 degrees. Okay, and I could find my direction cosine off the z-axis, 928 over 1416, and I get 49 degrees. So if I wanted the direction cosines, I could take these, take cosine of 116. I could make this a unit vector. It would be the same unit vector as if I took 612 divided by 1416. So now we need to go back and find the moments. Okay, so this is the trickier part. The trickier part is always where we have to find moments. So let's start again. I want to sum moments about the x-axis, and I'm going to call right-hand rule, okay, thumb in the direction of positive, rotation, positive rotation. So this direction will be a positive moment. If I look at this x component, parallel cannot cause a moment. If I look at this z component, I can see with respect to A, which is on the x-axis, that it is offset. So if I were looking at it head on, if this is my x-axis coming out of the page, and here is point A, this z-axis is actually acting, okay, offset, and it's pulling up, and it has a distance of 30 millimeters. So that would be, remember, vectors go all the way up and down. Okay, so that would be causing a moment about the x-axis. And according to right-hand rule, it is positive. So I have 700 sine 60 times 30. Let's rewrite that. Times 30 millimeters, or if we want to, we could call that 0.03 meters. And we're going to go ahead and change it to meters because this applied moment is in units of newtons and meters. So we need to make sure that we have consistent units. Okay, so we're done here. Now let's look at this 600 newtons. Okay, remember it goes all the way through. It's a continuous force vector. It is actually perpendicular, has a perpendicular distance back down to that plane on the bottom. It would be causing, if I'm attached, if this angle is attached here on the x-axis, and I were to pull on this angle, we can see it would rotate kind of clockwise about this angle, clockwise rotation, and that's going to be a negative. So we have negative 600 newtons times 0.04 meters. Okay. Now we need to deal with these three. If I look at the x component, it is running parallel to the x-axis. We are not causing a moment. If I look at the z component, it's going straight up and down. If I'm connected on the x-axis and I pull up on this angle, it is going to rotate. It's like opening a door, opening a door. So I have the x component, 500 newtons, sine 40. It is going to cause a positive rotation about the x-axis, and its perpendicular distance, if I were to look at this going all the way down, okay, its perpendicular distance back is 120 millimeters, which is 0.120 meters. If I look at this y component, again, it's a door hinge. I'm attached on the x-axis, and I'm going to pull in the y direction. It would be like if I made that vector just continue in space and I pulled on the back of this angle, it's going to want to rotate negative 500 newtons cosine 40 cosine 45, and its perpendicular distance is 0.1 meters times 0.1 meters. Okay, so now we need to deal with this moment. Okay, this moment that's being applied is being applied at the same angle that this force is being pulled. And so when we look at that, we have to understand that this moment also has x, y, and z components. And we've already figured out what those components are going to be. So if I am looking at the x component of this moment, okay, the x component, it is going to have the same cosine 40 sine 45. Okay, and I can see that it's rotating. Okay, it is rotating positively. So we are going to have plus 25 Newton meters, okay, times cosine 40 sine 45. That's how we get to the x component. And because we are already looking at a moment of Newton meters, we don't need to multiply it by distance. It is causing that rotation. So I have 700 sine 60 times 0.03 meters minus 600.04 plus 500, okay, sine 40 times 0.12. And if we sum these out, I get 24.6 Newton meters. And this is where if you used millimeters instead of meters, it would mess this number up. So because it's positive, I know that it's twisting the hinge back around, you can see, this way. Okay, so now I need to do the same thing, sum the moments about the y-axis, okay, using right-hand rule rotation. And we're going to do the same process. I can see that this x component would cause rotation about the y-axis, and we're specifically looking here at A. So if I'm looking, it would want to rotate around the y-axis. We are going to have 700 newtons cosine 60 times its perpendicular distance is, okay, if we are going about the A axis, I mean this A point, what is this distance up? Okay, and we can see that perpendicular distance is 0.1 meters. It's also positive this way, it's rotating backwards, negative. Okay, the Z component, will it rotate about the y-axis? Here's my y-axis, I'm pulling up, it's actually going to rotate towards me. Except that we're no longer looking at this y-axis, we are looking at the y-axis as it passes through A. So this little knobby, if you look at the picture, here's A, here's the knob. So it's going to cause a rotation into the page, which is negative minus 700 newtons sine 60. And now we need to look at its perpendicular distance. If this is going up and down, that's my z, okay? The distance back, okay, the distance back is 0.06. Okay? Y force will not cause rotation about the y. But here, y force won't, but both the x and the z will. So if I look at the x coming in this direction, perpendicular back down, okay, perpendicular back down is 0.08. So let's look at negative 500 cosine 40 sine 45, 0.08 meters. Okay, this z, if we're looking at the y-axis, we can go back over here. The z is actually on the back side of A, so it's going to cause a rotation that's positive, plus 500 newtons sine 40 times, okay, and what is its distance? We're on this back side, and we're coming to A, 0.05 meters. And then we need to include the y component of this applied moment. So we have 25 Newton meters, and the y component, cosine 40, cosine 45. And is it positive or negative? Okay, so we can see it's twisting kind of back and twisting towards us is positive, so that is also negative. And if we add this up, the resultant moment about y is negative 90.5 Newton meters. So that means if I'm looking at the y-axis, we're actually rotating back that way. So now let's look at summing moments. Z-axis up, right-hand rule. This is the resultant moment about the z-axis that's passing through A. So we have to go back to our picture. If we're going through A, the z-axis, okay, is parallel to the axis in the z direction. Because we are offset, this x component will cause a moment about the z-axis passing through A. And it will be positive. So we have 700 newtons, cosine 60, and its perpendicular distance back is 0.03 meters. Okay. If we want to look at the y component of this force, it can also twist around the x-axis. And because this little knob, here's the knob, here's point A, here's the axis, z-axis going through point A. Okay, we're pulling this way, it's going to cause a rotation, positive rotation. So we have plus 600 newtons. And then we can see we're offset by 0.06 meters. Okay, now the z component of this is parallel to z. It's not going to cause a moment, but both the x and y are offset. Okay, they are both offset. And so we are going to get negative 500 newtons, cosine 40, cosine 45, that's the y component, plus 500 newtons, cosine 40, sine 45, and its distance is 0.12. That's the x component. So we now need to look at the z component of this moment here, and sine 40. So we get 25 Newton meters, sine 40, and now we have to decide, is that a positive or negative moment? So if we're going up, okay, positive moment is wrapping this way. If I look at how I'm wrapping on here, I can see that we're wrapping this direction. So as I look at that X component, it is going down. My thumb is now going down. I don't know if you can see that, it's going down. So it is a negative. When I add all of these up, I get 49.4 Newton meters. That tells me my resultant is wrapping right-hand rule. So I could write this as my resultant moment about A is 24.6I minus 90.5J plus 49.4K Newton meters. I could also give you the magnitude, and it's going to be 106 Newton meters. So depending on whether we want Cartesian vector with the x, y, and z components or the magnitude. Okay, so I know this was a really long problem the way I set it up. If you have any problems on the 3D things, please make sure you're visiting with the TAs.